The saturated hydraulic conductivity is an important property of the subsoil. Together with the hydraulic gradient, it determines the volume flux density or specific discharge in the subsoil by Darcy's law. There are many techniques to estimate the hydraulic conductivity of the subsoil. All these techniques have their advantages and disadvantages. In practice, regardless of the selected technique, it is hard to obtain a precise estimate of the saturated hydraulic conductivity. This picture shows you the principle of the Constand-head permeameter for measuring the saturated hydraulic conductivity in a laboratory setting. You have a core sample in a metal casing, which you have taken in the field. Typical dimensions are a length of the core sample of 5 centimeters and an area of the core sample with a diameter of 5 centimeters. So it's a 100 cubic centimeter core sample. You can establish L and you can establish the value for A. This side of the core sample has a hydraulic head H1, simply the level of the water here. And then let's take the bottom part of this apparatus as your reference level. And this is H1, and the water flowing out of the system has a hydraulic head of H2. So the hydraulic head difference, H2 minus H1, the hydraulic head to which the water flows minus the hydraulic head from which the water flow dispatches, H2 minus H1 is a negative number. These are all positive numbers. We have a minus sign here, so your volume flux here is a positive number, and that's correct because the water is flowing upwards. You can simply determine this volume flux by simply catching the water here, and then you can determine the volume per unit time. So you know all the variables, and you can simply figure out what your saturated hydraulic conductivity is by using Darcy's law. Here we have a Constand-head permeameter in the laboratory. As you can see, your measurements are not limited to one subsoil core sample, but you can insert many of these. You can determine the volume fluxes here, and then simply by applying Darcy's law, you can figure out what the saturated hydraulic conductivities for these subsoil core samples are. Another measuring technique, also involving the use of one or more core samples of the subsoil, but usually performed in the field or during field work, is the Kopecky field method. A bottle is filled with water and closed by a cork with 2 open tubes. The bottle is then turned upside down and water is fed onto the subsoil sample as shown in this figure. The short tube lets the air in, while the larger tube lets the water out. When the water above the subsoil core sample reaches the outlet level of the larger tube, the water flow from the bottle is temporarily halted. In this way, a constant water level above the subsoil core sample is created, with water infiltrating from this water layer into the subsoil core sample. After the subsoil core sample is water saturated, and as soon as the volume flux Q attains a constant value, the hydraulic conductivity of the subsoil sample can be determined again by application of Darcy's law. Note that the water flow through the subsoil sample is downward, and that Q, the volume flux, thus has to be assigned a negative sign. As outflow from the subsoil core sample is under existing air pressure, the pressure head at the water dispatching end of the subsoil sample equals 0 meter. If we take the bottom of the subsoil core sample as the reference level, The hydraulic head at this water dispatching bottom end of the subsoil sample thus equals an elevation head of 0 meter plus a pressure head of 0 meter, totaling 0 meter. On the water receiving upper side, the hydraulic head equals an elevation head of L plus a pressure head of P1 divided by rho G. Both L and P1 divided by rho G being positive numbers. The difference in hydraulic head thus equals 0 minus, in between brackets, L plus P1 divided by rho G, close the bracket. So 0 minus L minus P1 divided by rho G. The hydraulic gradient equals the difference in hydraulic head divided by the distance. The distance is 0 minus L. Insert all of this in Darcy's law and you will get this equation. And these pictures are just to give you an impression of the Kopecky field method as used in the field. Another method to estimate the hydraulic conductivity is by using a falling head permeameter. We have an upper and lower chamber filled with water. Before the test, we add water to the upper chamber until the soil or sediment, the porous medium in the core sample, becomes completely saturated. The water leaves the lower chamber, as shown here to the right. We start the test by shutting the water input off. The water level in the upper chamber will start to drop. As the water drops, the volume flux of the water is going to decrease as the hydraulic head level drops and the hydraulic gradient decreases. We measure the drop in height in the upper chamber and the time this takes. To estimate the hydraulic conductivity K, we use the below equation. This equation is derived by combining Darcy's law and a continuity equation. Darcy's law is given here. Q is the volume flux in cubic meter per day, and A is the cross-sectional area of the sample in square meter. We take the top of our lower water chamber as our reference level, H in the equation, and as shown here is the diminishing negative hydraulic head difference, negative because the difference in hydraulic head is the hydraulic head to which the water flows, minus the hydraulic head from where it was dispatched. And L is the length of the porous medium sample that is resisting the water flow, the length over which the hydraulic head diminishes. H, a negative value over L, a negative value, thus is the diminishing hydraulic gradient, a positive value. Q thus has a negative value, the water is flowing downwards. Q in cubic meter per day is also equal to the change of hydraulic head, dH, with time, dt, in meter per day, multiplied by the cross-sectional area small a of the upper chamber standpipe in square meter. As dH is negative and dt is positive, Q has a negative value, the water is flowing downwards. Q of Darcy's law and Q of this equation are combined to give this equation. We can rewrite the equation by moving t to the left of the equation and all variables containing h to the right. From 0 to t seconds, the hydraulic head drops from H1 to H2. We integrate between the time boundaries of 0 and t to the left and the hydraulic heads H1 and H2 to the right. As the standard integral of 1 over h is ln h, we obtain this equation for t. We can reorder this equation to find the saturated hydraulic conductivity K. And instead of using ln, we can rewrite ln to a logarithm with base value 10 by multiplying by 2.302. Some finalizing notes on Darcy's law and the saturated hydraulic conductivity K. Darcy's law is limited to laminar flow situations where water can macroscopically be regarded to flow in parallel layers with no disturbance between the layers. Thus, Darcy's law works well for groundwater flow through media that resist water flow, such as sediments. There are many techniques to estimate the hydraulic conductivity of the subsurface. The set of techniques varies from laboratory tests involving core samples taken from the subsurface, as just shown, to field techniques such as borehole tests, pumping tests, and tracer tests. All these techniques have their advantages and disadvantages. The accuracy with which we determine the hydraulic conductivity of a subsurface core sample is first of all determined by the accuracy with which the core sample itself is collected. In principle, the subsurface core sample should be fully undisturbed, but in practice this can never be fully achieved. Collecting a good sample is an art in itself which can best be explained in the field. In any case, determining the hydraulic conductivity from a badly collected subsurface sample is useless. One should also keep in mind that the cores used for sampling are usually quite small. The cylinder-shaped cores often have a diameter of 5 cm and a length of 5 cm, establishing a volume of 100 cubic centimeter. Even if the sample is collected with great accuracy, the determined hydraulic conductivity only holds for this relatively small sample of the subsurface. Also, the sample volume may well be less than the representative elementary volume for the hydraulic conductivity. Collecting samples should always be accompanied by extensive field observations stating the conditions of the subsurface, especially with respect to the occurrence of cracks, number of cracks, depth of the cracks, as the larger or deeper cracks cannot be sampled in cylinder-shaped cores. One should take a sufficient number of samples to determine the distribution of the hydraulic conductivity values, and from this the best statistical average and standard deviation. To establish the hydraulic conductivity for a larger area, pumping tests are used where the hydraulic conductivity is related to the pumping rate and the differences in hydraulic head this causes.